As the microscope has already been set up for the EELS and EDS spectrum image acquisition, it is very straightforward to also acquire 4D STEM data. All that is required is to just change the filter from EELS mode back to F10 by clicking on the F10 button in the microscope UI, and a convergent diffraction pattern is projected onto the GIF camera instead of an EELS spectrum. The F10 button is blue, as I've already switched to F10 mode. At the moment, I'm looking at a live ADF image of the bismuth ferrite sample. I'll quickly rotate the scan using True Align and focus using the focus loop as we did before. Now we need to set up the spectrum image. I want the software to blank the beam after the SI capture is complete. To enable this setting, click on the Settings button in the SI Acquisition palette and then make sure the blank beam checkbox in the SI Setup window is checked. Next, check the camera setup. I'm currently using the camera in HDR mode with 2x binning. To verify if these conditions are good for an experiment, just start a live camera view. At the moment, the energy selecting slit is inserted and the width is 20 eV. By allowing only elastic scattered electrons to pass beyond the slit and form the diffraction pattern image, the contrast is improved. Look at how the image contrast is reduced when the slit is retracted. The 4D STEM, STEM EELS, and STEM EDS acquisition workflows are the same, so the next steps will look familiar. Switch the scan from search to preview mode and make sure the target signals are enabled. EDS and seabed are both blue, so no changes are needed here. Next, click on 2D Array in the Spectrum Imaging palette to add a Spectrum Image ROI to the ADF image. I'm going to move the Spectrum Image region slightly, as I just want to collect data from STO and bismuth ferrite. I'll also change the pixel size to 1 nanometer in the SI Acquisition palette. 6.2 milliseconds is the fastest frame rate for 1K HDR imaging, so I'll leave the pixel time unchanged. Live map is still enabled. I want to use the same EDS mapping parameters as we used previously, so I won't make any changes. All that is left is to click Capture and acquire the new dataset. Just as before with EELS and EDS, live mapping is a great way to monitor the results in real time. The software is also showing the live seabed image and live EDS spectrum as the spectrum images are captured. Again, as before, the spectrum image objects that were just acquired are linked. If the SI Picker tool is used to extract data from one of the cubes, the software will automatically show the data from the equivalent pixels of the linked object or objects. Orientation maps or virtual images can be created from the 4D STEM data. To generate a virtual HADAF image, right-click on the extracted seabed pattern and select the Annular Mask tool and left-click on the image to place the mask. The default mask placement will be at the image center. This seabed pattern is not centered at the image center, but this can easily be corrected using the Diffraction Centering tool. Right-click on the image again and select the Assign Center tool. Now just left-click at the diffraction pattern center and the mask position is adjusted to the new center. With the diffraction pattern still selected, go to the Map submenu in the SI menu and choose Signal Dynamic to create a map. The STO region currently shows bright contrast as the bright field disk in the seabed pattern is in the masked area. Dynamic maps respond dynamically to changes in the mapping parameters. As soon as any changes are made to the inner and outer angles of the mask, the map is recalculated. Look at how the contrast becomes inverted as I exclude the bright field disk by increasing the inner angle of the annular mask. That's all I want to cover for now, so I'll wrap things up. Over the course of this 3-part tutorial, I've demonstrated a fast, simple, an easy workflow for elemental mapping and 4D STEM using GMS 3.4 and the GIF Continuum. All of the setup, data capture, and mapping that I've shown can be completed in around 15 minutes, which hopefully you can reproduce and improve on in your own labs around the world.